All right, welcome to the final lecture of ECE 164 on analog integrated circuit design. So today what we're going to do is recap several of the key concepts that we've learned throughout this quarter. So we started off by talking about how integrated circuits are fabricated, going from the idea of using masks with photolithography and then subsequent processing steps that may include implants, growths, depositions, or polishing steps. And then this process is repeated many, many times for each of the different steps in the fabrication process. And really the big benefit here is what we call the economy of scales. And that's that when I make one of these integrated circuits, I make them on a wafer. And this wafer can be anywhere from 8-inch to 12 inches or even larger now. And this means that I'm not making one chip at a time, but I'm making hundreds or thousands even of the same chip at the exact same time. And so if we look at some of the different devices that we can make, here is an NMOS transistor. Again, we're in a P-type substrate. We would use implants in order to put down the source, the drain, and then a body contact. These are diffusions. That is that we're doping the P-type substrate with additional impurities in order to increase the resistance and or change the type from N-type to P-type, i.e. excess of donors versus excess of acceptors for electrons. Then we would do the gate oxide, and then finally the metal electrode or the polysilicon gate, and then start to work on vias and metallization for the back end of the line. So collectively, this whole process here is what's known as the front end of the line. Everything above this in terms of the metallization and the contacting is known as the back end of the line. So for an NMOS, we start off and we make the device directly in the P-type substrate. For a PMOS device, we want the majority carriers here to be holes, and so we need to put this inside of an N-type well. So we have an N well, we have P plus source, P plus drain, and then a body contact that is again N plus. Okay. Remember here that the plus and the minus on the doping indicates the amount of dopants that are present. So P plus means that we're doping this very heavily P-type. P plus plus means that we're doping it to the degenerate state. Okay. So that's how to make an NMOS and a PMOS. We can also make what's called BJT transistors or bipolar junction transistors. The best kind are what are known as vertical PNPs, where the entire BJT action happens vertically. The reason why these are better is because the base width that is here can be very narrow, and so we get high performance out of these transistors. However, most CMOS processes cannot make a native PNP in the vertical orientation like this, and we instead have to have lateral PNPs, which have significantly worse performance. We can also make passives. So in the case of resistors, many different ways of making a resistor, but here we're showing one way where we have a diffusion resistor. So we're literally using the resistance of this diffusion material here with two contacts on either end. We can also make a lot of different capacitors. Shown here is a metal oxide metal or a MOM capacitor where we're using two adjacent metals, in this case what looks like metal 1 and 2, and the insulator or the oxide material between them to form a parallel plate capacitance. We spent quite a bit of time talking about the notion of process variation. Simply put, the way that we draw all of the transistors and when they come out of the fabrication, they're not going to be identical. And so there's variation in each of these different parameters. And the variation can be bucketed into kind of two different categories. First, we can have what's called corner wafers, where all of these parameters, i.e. all of the threshold voltages for NMOS or PMOS will change together. These are known as corner lots. So in the case of a slow corner, that would mean that the threshold voltage was increased over the nominal case. And for a fast corner, the threshold voltage would decrease over the nominal case. So the way to think about this is that if I had a fixed gate overdrive voltage, excuse me, a fixed gate voltage, not an overdrive voltage, for the nominal case, if I was to go to the slow case, I would have lower overdrive voltage, which would make the device have less current and appear slower. For the fast case, I would have more overdrive voltage, the device would have more current, and it would appear faster. So the same is true of all of the other parameters in terms of the transconductance, poly resistance, as well as the capacitance between, in this case, two polys. In addition to having this global process variation, all of these have temperature coefficients associated with them, which we need to take into account when we start designing temperature robust circuits in order to leverage this temperature coefficient. The other process variation that we can see is what's known as random process variation. So in the case of random process variation, this is something where we're going to look at devices on the same chip having variation, so that if I have two NMOS devices, if they're both in the slow corner, that means that they'll have the same VT. This other variation is random variation, and we can calculate the distribution of this using what's known as Pilgrim coefficients. So Pilgrim coefficients allow us to calculate the variation in the device using these coefficients divided by the square root of the area of the device. And so if we wanted to calculate, for example, two transistors and we wanted them to have VT matching within a particular tolerance, we could use this sizing parameter in order to adjust the size such that we guaranteed by design that the variation in the threshold voltage was less than, for example, 5 millivolts. All right, then we spent a lot of time talking about the actual characteristics of the transistors, understanding the different regions of operation, when the device is in triode, when it's in saturation, when it's in cutoff. We even spent a little bit more and talked about some of the advanced techniques, such as when the device is in sub-threshold. And we know that in that case that the current doesn't actually go directly to zero, but that we do have conduction below VT. We derived both of these equations in terms of their fundamental device physics, so we understand where all of the terms come from and how they're all set up. And then we started to talk about some more advanced second order behavior of these devices, things like channel length modulation, which cause there to be a finite slope of this IDS curve, which results in us adding a band-aid to our square law model equation with this 1 plus lambda VDS term. We also talked about the body effect. Simply put, the body effect allows us to modulate the threshold voltage of the device by applying a DC voltage to the body of the device relative to the source. So doing this, we can either make it easier or harder to invert the channel. We also know that we can use this from a small signal perspective by applying a AC signal at the body and getting additional transconductance from this device, a GMB term in our small signal model. So talking more about our small signal model, we built up the small signal model over the course of a couple of lectures, including all of the various different capacitances of the device, as well as the transconductance from the input, the transconductance from the body, and this output impedance. Fundamentally, a MOSFET needs this capacitance. It needs CGS to operate. It's not a MOSFET if it doesn't have CGS. All of the other capacitors are what we would call extrinsic capacitors. They're parasitic capacitances from how we manufacture the device, and we have to deal with them, but in an ideal world, with an ideal MOSFET, we would not have any of these capacitances. Okay. We talked a little bit about how all of the capacitances change as a function of the operating point. So if we're in subthreshold versus triode versus saturation, each of these capacitances has a different value. We use this table in order to understand the capacitance at each of these points. We then spent quite a bit of time talking about Miller's theorem, in particular with respect to this CGD capacitance. So the CGD capacitance is problematic in the sense that it couples the input and the output, and so it allows signals to race forward from the input to the output. We also saw from feedback lecture that this provides a way of feeding back part of the output to the input. That is to say that it's bilateral in its feedback. It doesn't just allow one direction for the feedback. In order to make sense of this, we first did KCL, KVL to understand where all of the poles and the zeros are in the circuit. However, we quickly came to the conclusion that it was intractable to continue down this route, given the complexity and the entropy of these expressions. And so we set out for ways to deal with this complexity that allowed us to get back of the envelope estimates without having to solve, full KCL, KVL and trying to make sense of these expressions. And so this brought us to the idea of Miller's theorem. Miller's theorem states that we can take an impedance that's in feedback between nodes V1 and V2, or 1 and 2 in this expression here, and we can translate them into an impedance shunted to the ground at the input and an impedance shunted to the ground at the output. In order to do this, we need to modify these impedances from Z to Z divided by 1 minus K at the input and Z times K divided by K minus 1 at the output, where K is the gain of this circuit. Now, Miller's theorem is exact in how it calculates this, and it is provable in the sense that we can show via circuit theorems that it is always true. Okay? The difficulty is that K is often not a constant. K is usually frequency dependent. And when we want to use this, oftentimes what we'd like to do is we'd like to use this in conjunction with Miller's approximation. Miller's approximation says that this K of S gain term can be substituted with its low frequency, often DC, value if the dominant pole is much less than any of the zeros that are in this circuit. And so simply put, what we're saying is that if we were to look at a pole zero plot here and have several poles and several zeros on this plot, this expression, using Miller's theorem, I can precisely figure out what this dominant pole is, that is the lowest frequency pole, but I can't do anything about any of the higher order poles and zeros because after I hit this term, after I hit this pole, this gain expression is going down. Okay, and so this gain expression is no longer valid to calculate the precise frequency for any of these higher frequency poles or zeros. We also talked about another technique known as zero value time constants. Zero value time constants allows us to again estimate the 3 dB frequency of a circuit. It says nothing about any of the higher frequency poles or zeros. It is again just like Miller's theorem. However, it's a little bit more general in the sense that we don't just have to have a capacitance tied between the input and the output. Fundamentally, what we're doing is we're saying that there's a single pole in the circuit, and so by doing that, we can estimate this B1 coefficient, and the B1 coefficient will give us the bandwidth of the circuit. And so in order to solve for the B1 coefficient, we have this cookbook procedure where we first condition the circuit. This comprises removing all of the AC coupling and decoupling capacitors, shorting the independent sources, independent voltage sources, and opening the independent current sources. So simply what we would do in order to get into small signal model. Then we're going to consider each capacitor separately and find the driving impedance that that capacitor sees. Notably, ground is not a special node. Anything that's connected with ground is like any other node in this particular analysis. Then we're going to compute the time constant seen by that capacitor, where tau of j is going to be equal to Rj Cj. We will repeat the above for all of the capacitors in the circuit and estimate this coefficient B1 by summing all of these time constants. And then the 3 dB bandwidth is simply 1 over B1, or 1 over the sum of the time constants. And so we did several examples of this in class. We found this to be a very powerful technique, again, at estimating the 3 dB bandwidth, and more importantly, guiding us in our analysis of which time constant was limiting the performance. So in the case of the 3 dB bandwidth, we can find which of these time constants is limiting the performance of the circuit and focus our effort on that resistance and or capacitance in order to improve the bandwidth of the circuit. We talked quite a bit about elementary amplifier stages, starting with the common source amplifier, which essentially acts like a voltage-controlled current source and makes a very good amplifier when we can terminate this with a high output impedance. And so essentially what we're doing is we're taking a voltage at the input, turning it into a current with this transistor, essentially making a transconductance, then converting that current back into a voltage with the impedance at the output. We talked quite a bit about a common gate amplifier. These are typically used when we're trying to have a low input impedance, i.e. for something like a current. And we can use these common gate in conjunction with the common source as a cascade in order to increase the output impedance that we see from this device. So we'll stack a common source and a common gate transistor and then put a load on top of that. Then lastly, we talked about a common drain amplifier. These have very low output impedance, and so they're typically good for buffers or DC level shifting. In particular, you'll find these most common at the output of amplifiers. Then we started talking about multi-stage amplifiers, combining the several of the previous stages together in order to get properties that allowed us to manipulate both the input and the output impedances while also providing the necessary gain that we're looking for. And so a couple of examples of this, we talked about a common source amplifier. The idea here is that we would simply cascade two of these stages together. The properties are very similar to what we get from a common source. We're going to get a lot of voltage gain. We have a high input impedance, and we have a relatively high output impedance. We can add the cascade, namely we can add a common gate stage here to this amplifier and here to this amplifier. This allows us to, again, get a lot of gain, but also increase the output impedance. So we're going to have higher R out from the cascade. We then talked about a common source, common drain. The idea here is that we make gain in the first stage of this amplifier, and then in the second stage, we simply use this to drive a smaller impedance. And so we're hiding the output load from this high gain stage. Whereas if we didn't have this and we directly connected the load would reduce the output impedance here, that we would essentially reduce all of the gain. Okay. This particular amplifier has a high input impedance, again for a MOSFET, and a low output impedance because we're looking into the 1 over GM of this common drain amplifier. We talked quite a bit about common gain, common source amplifiers. We saw this in a couple of the homeworks as well. The idea here is that we're trying to take a current and convert a current to a voltage at the output. And so this is what's known as a transimpedance amplifier. Voltage out, current in. in this case, since the input is a current, we're trying to have all of the current go into the amplifier itself. And so we want a low input impedance. Since we have a voltage at the output, we're looking for a moderate to a high output impedance. All right, then we started talking about differential pairs. One of the most common circuit blocks that you'll encounter in any integrated circuit design. We started off by describing how we could break the input into its positive and negative components, or differential and common mode components. So this is a nice way of analyzing the circuit. In particular, when we're going to use half circuit analysis, we'll want to put it into this type of structure where we write that the inputs are the sum of a common mode and a differential mode component, and then we can analyze the common mode and differential mode response separately. We first described the large signal behavior of this device, beginning with the output currents, ID1 and ID2, with respect or normalized to their tail current. And we showed this notion of what's called complete current steering. That is when we're directing all of this tail current towards one side or the other. And this occurs when the differential mode voltage is greater than plus or minus the overdrive voltage times the square root of 2. From a small signal perspective, this essentially looks like a transconductance, a GM, where the GM is equal to 2ID divided by VOV, where ID in this case is half of the tail current. And so we get this final expression here that the transconductance is equal to I tail divided by VOV. As I mentioned earlier, if this circuit is symmetric, then we can analyze it with the half circuits, and we can find the common mode and the differential mode response separately, which usually dramatically simplifies the amount of effort that we need to put into analyzing this particular circuit. We talked quite a bit about current mirrors for biasing, the idea going back to the process voltage and temperature robustness of these circuits, that we would rather use other transistors that are physically located very close to the transistor that we're trying to bias, in this case, these two transistors here. And what this allows us to do is the diode connected device, quote unquote, computes the right voltage that we place at the gate here in order to have these two currents match. So I out is equal to IN. And then we can play with the sizing of these transistors, in particular, multiplying this current up or down by sizing this device smaller or larger. And so if we look at the ratio of the output current divided by the input current, we see this expression. Importantly, a lot of the process parameters, things like mu, cancel, things like VGS, VT, all of these cancel. And so at the end of the day, what this really surmounts to is that it's a ratio of the two widths of the devices. We talked a little bit about this, but just to remind you, oftentimes we want to leave the length of the device fixed. While it looks like it's a free variable to change here, in practice it changes a lot of the second order effects of this device. And so you'll often leave these two devices to have the same length and simply change the width in order to mirror the currents around for this ratio. We then started adding some more advanced features to these current mirrors. In particular, what we're trying to do here is increase the output impedance that we see from this structure in order to make it higher. And higher output impedance makes this a more ideal current source. Whereas here, we know that there's some finite R out of this device, and this R out modulates this current I out through the device. And so here, we're trying to increase R out such that we have less modulation of that current. The way that we've done this is by adding this cascode structure here. So we've added the cascode device, and in order to bias this, we're looking at trying to minimize the compliance voltage. And so the compliance voltage is the minimum voltage that we can apply at the the node here and still keep both of these devices in saturation. We showed after a little bit of analysis that the minimum voltage would be 1 VOV here and 1 VOV across this bottom device, such that the total was 2 times VOV. However, in order to get this 2 VOV, that meant that we needed to have a slightly more complex biasing structure. So in the case of this top one, we were able to simply diode connect the device. Here, we're not able to just diode connect the device because that would create this voltage much larger, and we would essentially end up with a VT term in here that we're trying to get rid of. And so that's where this idea of the magic battery here comes in. We're trying to bias this particular voltage at 2 VOV plus VT such that this node is biased at VOV. And when we go up, we end up with this minimum compliance voltage without that second VT term in that. And so we went through a couple of different structures in order to generate this magic battery voltage that gave us the cascode voltage equal to 2 VOV plus VT. Then we spent a little bit of time talking about how one would mirror currents around, i.e. taking a diode connected device, copying that to other transistors that were in parallel, and then using these to mirror the currents around to bias up much larger structures, or even send currents across the entire chip. Again, sending currents is much safer than sending voltages, in part because of the low impedance nature that we have. So here, this sees a 1 over GM impedance. And so any disturbance on this line will settle out very quickly as compared to a voltage bias line, which is typically high impedance. Then we talked about feedback, both positive and negative. However, we spent the majority of the time talking about negative feedback. Negative feedback has many benefits to circuits. One, it allows us to build very high gain forward path amplifiers. And then by using passive devices for the feedback network, we can set the closed loop transfer function of this. The feedback itself helps to desensitize the circuit to variations in the open loop gain. It helps with the distortion, and it also helps in some sense with biasing because we can use feedback in order to handle process variation. The closed loop transfer function from this block diagram can be derived as A divided by 1 plus AF. We talked a lot about this AF term here. This is essentially the loop gain. And the loop gain is very important. It affects a lot of the stability of the circuit, but it also is what changes the input and the output impedance. And so when we want to analyze the stability of the circuit, we need the loop gain, and for the port impedances as well. We talked about a couple of different ways of getting this loop gain, and one of the more advanced techniques that I showed you was this concept of return ratio. So in return ratio, we fix a few of the issues with this top model, namely that the circuit in the feedback does not have to just be unilateral, meaning that we're only feeding signal back to the input, but that we can also have signal that gets fed forward from the input to the output. That's captured in this model with the D term here. In addition to this, this particular model is quite nice because it allows us to simulate each of these parameters. So I can simulate A infinity, I can simulate D, and I can simulate the return ratio here, which makes it much more amenable to general purpose analysis rather than having to try to fit things into this block diagram, which don't always fit nicely. In order to calculate the closed loop gain, we derived that the closed loop gain is equal to A infinity times the return ratio divided by 1 plus the return ratio plus this feed forward term here, D, divided by 1 plus R. In order to get each of these individual components, we simply analyze the circuit. For the return ratio or the loop gain, we take a transconductor, we cut the circuit at that transconductor, insert a test source of the same type, and then look at how much is returned back at the source. For the A infinity, we're going to look at the closed loop response of the circuit, so S out divided by S in, when the transconductance or the gain element is infinitely strong. Okay, and so that's why it gets the name A infinity. For the D, the feed forward term, again, we're going to look at the S out divided by S in term when the transconductor in this case, or the gain element, is turned off, so it is 0. Okay. Again, the nice part about this is rather than just doing KCL, KVL, and getting the closed loop gain, we end up with this very important loop gain term along the way, which again lets us assess the stability of the circuit in addition to finding the closed loop gain of the circuit. All right, so looking at your journey as a circuit designer, we started off in ECE 65 and 102. We learned the fundamentals of circuits. We learned how to analyze circuits, but we didn't really learn how to synthesize circuits. Some of the more advanced courses in the undergraduate level and incoming master's and PhD level, the 160 series in particular, we start to teach students a little bit more tools on synthesizing circuits, that is, designing circuits. However, your journey is not quite complete yet. We offer a whole bunch of other courses beyond this, in particular for analog integrated circuit design. We have the 264 series, where we talk more about designing amplifiers, noise, PLLs, and also data converters. So if you are interested in circuits, I would strongly consider you to continue your journey and learn additional tools as you become a better and better circuit designer. All right, so the last few words of wisdom, please do study for the final. I know that it's open note, and so the tendency may be to not study before the exam and just rely on your notes during the exam. However, in my experience, this usually does not end well. You can't really learn these concepts just by reading the notes. You need to do the homework and actually think through planning them. Along that same line, really the value is in making a cheat sheet is that you focus on distilling down these complex topics into what you feel are the key important elements. And that's also my last piece of advice, is that you should focus on the concepts. There's no sense in trying to memorize these things either for this class or for your future as an analog circuit designer. It's much more important that you understand the fundamental concepts such that you can apply it to arbitrary circuits that you're going to inevitably encounter on the final and throughout life in your course as a circuit designer. Lastly, thank you for this course. I hope that you enjoyed it, and I hope that you learned a lot. Good luck on the final next week. Thank you.